when we look at prefixes, each prefix has a meaning. Right? So if we're asked the question, what do these prefixes mean? Centi, milli, micro? Well, centi is what? It's 100th. No. Yes. Brain fart. Yeah, centi is 100th. And then milli is 1,000th. Micro is a millionth. Okay, so it should be, let's see, 2, 3, and 6. Here we go. B. Sometimes when I do these reviews, I have a key. This one, I don't think this one is key. Yeah, it is. There it is, right there. Okay, I missed it. Yeah, that red A means answer. Okay, so that way I can check myself too while I'm going through it. And if my logic doesn't give us the answer that's here, then I have to think, why? Is that wrong or am I wrong? Okay, so that was number 1. Here we go. All right, which of the following pairs of measured numbers does each member of the pair contain the same number of significant figures? So to answer this one, you have to know the rules. How do you determine significant figures? All right, they're non-zero numbers, and then there are zeros. And they got 3 flavors of zeros. The zeros to the left are never significant. The zeros that are captured, surrounded by non-zero numbers, are always significant. And the ones to the right are only significant if there is an explicit decimal somewhere in that number. So we look for this. How many significant figures here? 1, 2, 3, 1, 2, 3, 4. No, ain't that one. There's 4 here. There's a decimal. See, that one's only got 1. So you got 1 and 4. No. How about this one? 1, 2, 3, 4, and 1, 2, 3, 4. That's it. Wait a minute. Each member of the pair contains the same number. Wait a minute. That one's got 1, 2, 3, 4. Oh, 3. Excuse me. Right. Speak up. Catch me if I'm wrong. Right. So that one's not it. And this one should be it because it's got the A in front of it. 2 and 2. Yep. That's it. The same number of significant figures. How would we write these in, while we're here, scientific notation? We write this one, move the decimal 1, 2, 3, 4, 5. So to the right is -5. And then we have 9.6. Okay. How about this one? That one would be 9.6 also. Except the power of 10 would be different. Because it would move 1, 2, 3, 4, 5 the other direction. So the one on the right is +5, and the one on the left is -5. Okay, I'm gonna have to scroll down because all this thing will do is page, and then chop the 3 off at the top. Get those 2 in there at the same time. Recording over it. Okay. The correct answer obtained from adding the measurements, these 3 measurements, add them together. How many significant figures do you have? Okay. Remember the rules? We've got 2 types of rules: add, subtract, multiply, divide. So if we want to work this problem, we need to line up the decimal points. Here we go. Add them together. And the first step is you just add them, right? Let your calculator do the work if you want. 2, 14, 17, 10, 19. Okay. Then you have to decide how many decimal places can I keep. Right here. The least number determines the answer. So now we have to round off to this one. That one's less than 5. It just goes out. And it's 19.7, which is 3 significant figures. So there it is right there. Color doesn't show up too well on this, at least from my angle. Well, okay, if I come around like this, it looks red. Yeah. Okay, so if we had, you remember the example I used for, what do you do with numbers that don't have explicit decimals in them? Well, you still have to line up the assumed decimals, but then to decide where you chop it off, you say, are the zeros significant or not? If you had like this one, and you had like that one, and that one to add together, right? You have to chop it off there because these are not significant. Okay, they don't tell you that in the textbook. Okay, 4. According to the dimensional analysis, there's that big pair of words again. Which of the following is the correct setup for the problem? How many milligrams are there in 85 kilograms? Okay, so if you're trying to do a unit conversion from milligrams to kilograms, oops, that, how would you set that up? It was 85 milligrams. Okay, we're in the metric system, so we only need to use decimal system. If we're going from milligrams to kilograms, do we know can we do it in one step? Well, we could, right? But to answer the question, all of these are in 2 steps. So what I think they're getting at is change this one to grams. Milligrams on the bottom, grams on the top. Right? Why? Because this is in the numerator and that's in the denominator. And they have to cancel and leave us with the target. So the ratio here is 1,000 milligrams per gram, or 10 to the minus 3 grams per milligram. And then to get to kilograms, right, we got to cancel grams and leave us with kilograms. The answer, the units that you're heading for, are always in the numerator. So to cancel grams and kilograms, we have 1,000 grams per kilogram. Right? Now, is that one of our answers? Grams per milligram. Wait a minute. Why didn't you stop me? That's supposed to be kilograms. Okay. Let's do this all over again. There we go. 10 to the third grams per kilogram, and then milligrams on the top, grams on the bottom, 10 to the third milligrams per gram. Now, that fits grams per kilogram. Okay. Actually, you can 85 kilograms. Test taking technique, eliminate the ones that can't possibly be right. So if you go to the first step and say, that can't be right, 10 to the third kilograms, right? Kilograms is bigger than grams. So you don't want 1,000 kilograms in a gram. Right? So you look at the first one, and that one's right. No, that one should be 10 to the 6th, actually. And that one's wrong too. So this one's the only one that could possibly be it. And then you just look over here and say, is that right? 1 milligram? Well, yeah, if you do this, that works. 1,000th of a gram is a milligram. So that's why B is the answer. So sometimes it takes a little, you have to stop and be cool, don't get frustrated, analyze it logically, step by step. Yeah.
So these are answers,
Uh-huh.
but should the 2 milligrams on the right side should it be grams or is it 7 grams?
You are right.
I just caught it because of like
That's a typographical error.
it doesn't cancel out.
Yeah, you're right. That should be grams. Let's see, is this a Word document? Oh, yeah, it's an image. I can't fix it.
If you move the image to the back, you can edit it.
I'm sorry.
I'm pretty sure if you move like copy pasted the images to the back, you can edit it from.
Move it to the back.
Yeah.
Like this.
Yeah, if it's texting, oh, well, no, it's actual, it's the image.
Okay. Yeah, I'm gonna have to. Let's see. I don't have a hard copy to mark. Let me do. Let's see. How would I mark this one out? Put a big X. Make it red. So I go back. I know something's wrong. Good catch. Okay. Let's see if we can catch them with another wrong. The density of an object is the ratio of what? Well, it's got a formula, right? Density is mass per unit volume. So you just find the one that matches. Ratio of mass to volume, here it is. That was right. And since it's a formula, you can manipulate it any way you want to, algebraically speaking. So if you know two of them, you can solve for the third one. I need to scroll out. Oops. Yeah, we do it like this. Then when I page, chop the other one off. Okay, if an object A weighs 6 grams and has a volume of 3 milliliters, and an object of 9 grams and has a volume of 2.25 milliliters, which one's denser? That's what they're getting at. So 6 grams, object A has 6 grams and 3 milliliters. So that'd be 2 grams per milliliter, right? Well, let's be too significant here. And then B is what? 9 grams and 2.25. 9 grams and 2.25 milliliters. Can I do that with my head? This ratio is 2 to 1. Right? For every one of those, there's 2 of these. So how about this one? That's closer to 4. That's about 4 to 1. So you can answer this question without a calculator. It says, B is less dense than A? No. B is twice as dense as A. Yeah. Seven. I should be writing those up here. Which of the following statements concerning conversion factors is incorrect? Okay, English to English conversion factors come from defined relationships. Yeah. The thing about the English system is you just have to know conversions. like 1 inch, 12 inches per foot. Or, I don't know, they don't use too much anymore, but 6 feet a fathom, right? Or 5,280 feet in a mile, or 3 feet to the yard. You just have to learn those conversion factors. That's the problem with the English system. Metric to metric conversions come from measured relationships. Well, yeah, they do, but they're a little more logical because they're all decimals. English to English conversion factors always contain exact numbers. Always contain exact numbers. Well, the ones I gave you were exact. Are there others? There are some that are not exact numbers. I'm trying to think of examples. They're kind of obscure, right? Most of the ones that we use day in and day out are exact numbers, like 1,760 feet, yards per mile is an exact number. Incorrect. English to English conversion factors. Oh, there's the key. Whenever you see always, in sciences, always is a rarity. Yeah, that was kind of cryptic because we really didn't look at any conversion factors that weren't exact. Now, English to metric would be a better choice. English to metric conversion factors, right, they're usually not. For instance, 2.54 centimeters per inch. Well, you know what? By our rules of significant figures, any conversion factor is considered an exact number, isn't it? Yeah, right. So that's a bad question. You can put that one away. You won't see that one again. Or one like it. Okay, let's move on to something worth tackling. Which of the following conversion factors would limit a calculation to 2 significant figures? None, because of what I just said. Conversion factors are always considered exact numbers. They have no limit on the significant figures of your answers.
Will always be an exact number.
Yeah, no correct response. Right? None of them would limit your answer to 2 significant figures. The temptation would be to say, here, there's 2 significant figures. But none of them actually limit your answer to 2 significant figures because conversion factors are always multiply divide. No. I just tripped myself up. Convert Celsius to Fahrenheit temperature. That's a combination. But that's a formula. It's embedded conversion factors, right? So it has this one as a multiply divide, and this one is an add subtract. But since they're conversion factors, they don't limit the answers. The answer is only limited by this one. So whatever this one happens to be, that's the one that dictates what happens here and what happens there. Okay. How about 9? Okay. These types of questions are extremely difficult to do in a timely manner on an exam. So any of this type where you have several statements and you have to say how many of them are true, those will be relegated to bonus questions. So if you don't have time, don't waste on those until you get the body of the test finished. You can read them if you want to. I mean, maybe something will click and you say, And then that's both. But we'll take a look at them anyway. Okay, we've got three statements. How many of them are true? In outer space, an astronaut may be weightless, but never massless. Okay, I'll go with that. You know, technically speaking, you're never weightless as long as you're in a gravitational field, what they call microgravity. You feel weightless, right? It's a relativity thing. And your body acts as if you're weightless, right? You start losing red blood cells, start losing bone mass, and it happens really quick. So that's why they put astronauts on an exercise regimen when they're in space to help trick the body into thinking there's some gravity every now and then. But for all intents and purposes, we can say this one's true. The metric system prefixes milli and micro differ in mathematical meaning by a factor of 1,000. Well, let's see, micro is 10 to the minus 6. Milli is 10 to the minus 3. Yep, that's 1,000 to 1 ratio. Right? You got 3 orders of magnitude. Yep. Has anybody ever used that expression before? An order of magnitude is a power of 10. So this one to the first power would be how many times, no, that's not right, compared to this one, right? A change of 1 to 6 is 5 orders of magnitude difference. In case you ever hear that again, it's not something we're going to use on an exam. I like to throw out these tidbits so you can impress people at parties. Okay, so this one's true. The addition of 273 to a Fahrenheit temperature reading will convert it to a Kelvin temperature reading. No way. It's got to be Celsius. Then you can add 273. And that'll convert to Kelvin. So only 2 of them are true. Okay. That's why these are really nasty questions. Because, I mean, they're worse than true false. And I hate true false. But this does get you to think. And contrary to modern educational theory, we want you to learn how to think. So many educators believe that we want to indoctrinate you. We want to make you good little robot citizens that pull the right lever in the voting booth. I'm adamantly opposed to that. To be a thinking human. Here we go. Here's another one. 3 statements. The measured number 2.410 times 10 to the minus 3 contains 3 significant figures. No, it's got 4, doesn't it? That 0 is significant. Okay, so that one's false. Specific heat of water is higher than that of most other substances. We talked about specific heat yet. Okay, so that wouldn't be a good question because we haven't even defined what it is. And if one of them slips by and ends up on a test, call me on it, right? We never studied that. That shows at least you're paying attention. Right? But this statement is true, actually. The specific heat. The specific heat, I'll just give it to you, is the amount of heat that a substance absorbs to change its temperature 1 degree Celsius. So if it takes a lot more heat to change the temperature 1 degree Celsius, that means its specific heat is higher. And the specific heat for water is one of the highest naturally occurring. So 2 is true. The equation 1 kilogram equals 10 to the 6 milligrams is correct. Well, let's see. 10 to the 3rd grams and then 10 to the third milligrams per gram. So yeah, 10 to the third times 10 to the third is 10 to the sixth. So that was true. So the two of them are true. But it's got a boogeroo right here we haven't covered yet. I don't know how that made it into the test bank. We haven't even talked about it. Oh, we got a bunch of these guys. Okay. The size of the degree is the same on Fahrenheit and Celsius temperature scale. Now, they're different sizes. What's the ratio of the sizes? 9/5. Right? For every 9 degrees Fahrenheit, you move 5 degrees Celsius. Right? That part of the equation is times C. So this is the ratio number for C, cancels out. And then the size of the Fahrenheit degree is smaller. I like it this way because I can look at those, you see those thermometers on the bank billboards. They flash Fahrenheit, they flash centigrade or Celsius. If they flash Celsius and I want to know what the Fahrenheit temperature is, I don't have time. I can't stop in traffic and wait for it to change. So if I see the temperature is, I don't know, 68. I know that 68 Fahrenheit, well, actually I'm working the wrong direction. If it says 20 degrees Celsius, I know that's 68, because I have it memorized. But if it's not, say it's 25 Celsius, then I know I just need to add 9 to that. And I know it's 77 Fahrenheit. Okay, or if it's the other direction, if it's cold in the winter, and say it flashes a temperature of 15, then I know it's 59 degrees Fahrenheit. Just subtract 9 from that. And it's based on that ratio. For every 5 Celsius, 9 degrees. I just need my anchor point, and this is my anchor point. I know 20 is equal to 68. I don't even have to calculate it. Okay, back to the problem. Let's see. That one's false. They're not the same size degree. The measurement 62,300 has an uncertainty of plus or minus 100. Okay, we didn't spend a lot of time on this one either, but the uncertainty refers to significant figures. It's only significant, well, actually, hold on a second, 62.3. Okay. The certain numbers are these two, right? And the uncertain one is this one. So if it's uncertain, then it's uncertain in that one. If we're taking a guess at this value, we'd either have to guess up to 4 or down to 2. So it's halfway in between. When you're actually looking at a measurement, you're looking at the average because there's no mark anywhere to tell you where that one is. So this would be off by 100. It could be high 100, it could be high by 1 or low by 1. This is the uncertain number. That's what that means. And that's true. But we didn't dwell on that in class. We just focused on the certain and uncertain. But this is an extension of that. Scientists know that's what that means, unless you specify exactly what the uncertainty is based upon your experiment. But if you just put the number up there, then it's assumed that you're uncertain in this one. It could be high by 1 or low by 1. The answer to the calculation 845 plus 1040 should contain 4 significant figures. 8.45 and 10.40. 5, oops, 8. And 8. Yeah, we get to keep all of those. That's 4 significant figures. So 2 are correct. Let me see. I'm going to skip these guys right here. Yeah. Because I think that horse is dead. So it's a beat any further. Okay. We did talk about isotopes, right? Okay. Just checking. 2 naturally occurring isotopes exist for the hypothetical element dipium. Well, what's the symbol? What would dipium be? There's no D up there. We could use D. Or we could use DI. Yeah, let's use DI. That's dipium. 25% of dipium atoms have a relative mass of 17 atomic mass units. 75% have 21.3. What's the atomic mass of dipium? So you remember how to do relative, calculate the average, weighted average atomic mass for an element. It's like doing your GPA. Right? We know that 25%, 0.25, is this one, 17 atomic mass units. And then the other one is 75% times 21.3. So we just need to multiply this one, multiply that one, add them together. Yeah, I guess I better do that. Let's see, 0.25 and 17 is 4.25 for the first one. And 0.75 times 21.3 is 15.975. Let's see, how many can I have up here? I can have 3 for that one, that's good. I can have 3 for this one, so it's going to be 16.0 for that one. And then we have 5, 2, 0, 2, 20.25. Oops, got to round it off. 20.3. Okay. Here's a lesson in test taking technique. Whenever you have multiple choice questions, and they're all definite answers. There are no squirrely ones in there like none of the above or 2 of the above and that kind of thing. If they're all just unique answers, pick the best one. And the best one would be this one, 20.2. Right, that's the closest to the answer that I got. That's how I would answer this one and move on. But the method is, got the method though. It's a weighted average of the abundance of the different isotopes. I think it's funny, they're always coming up with these, let's see, what was it? What was the movie where they had the element was unobtainium? Oh, that was, it was just on TV. I can't remember the name of the movie now. They're on the moon of this some distant planet, and it was already occupied by these tall creatures, and they had cloned or created bodies, but they had no mind in them. So humans would get in these pods and they would connect mind to the clones, and then they could just run all over the place. Otherwise, the atmosphere was toxic. What was the name of that?
Sounds like Avatar.
Avatar. Thank you. Avatar. Yeah, they were after this element called unobtainium. And for anybody who studied chemistry or physics, they know that it's impossible because that's everything there is right there. Right? Elements that are this heavy are all radioactive. They're unstable. Right? You couldn't hold them and they're very minute quantities. So when that scene comes in the corporate guy, the evil corporate guy, was holding a piece of the unobtainium, first of all, you couldn't have that much of it. And second of all, it'd be radioactive and it'd burn your fingers off. So, but I'm like anybody else. When I want to watch a science fiction movie, I go in recognizing that, you know, if I get caught up in it, then I come out the other end unchanged. But I can enjoy myself on the way. Okay, back to our problems. The correct electronic configuration for, let's see, 14, for this element, right? Chlorine, right? 17 protons. It's neutral, so it has to have 17 electrons. So you remember how to write out the shorthand, right? The lowest energy is 1s, right? Then you have 2s, and 2p, 3s, 3p. Let's see, we can use our periodic table. There's 3, 3s, 3p. Okay, that's all we're going to need. Right up to there. So this would have 2 in the s's, 2 in the s's, 6 in the p's. That's 10 of them already. So we need 7 more. 2, need 5 more. That's it. Okay. Or, well, no, you're going to have to write it this way. Right? We can't use the ultra abbreviated version, right? Where you back up to the nearest noble gas and use that as your starting point. That's your core. And then you go down and say 3s2, 3p, 1, 2, 3, 4, 5, 3p5. But you can use it to do the rest of them, right? These are both 1s's. This is 2s, 2p. This is 3s, 3p right over there is 5 places. So you can do it that way. Or you can draw the diagonal if you want. That's chlorine. Now, if I had said this one, what's the electronic configuration of that element? Not give you a symbol. You can still do it, right? Because, you know, if you know the number of protons, you know the element. Just look it up. That's chlorine. Okay, 15. Which of the following statements is consistent with the electronic configuration? 1 is 2, 2 is 3p6. 3p6. There are 6 electrons present in a 3p orbital. No, you can only have 2 electrons per orbital. This represents 3 orbitals. Right? So that's not right. There are 6 electrons present in a 3p subshell. That's a subshell. The orbitals are, for the p's, this is a subshell. And then the p's have 3 orbitals within them, x, y, and z. Okay. Or let's see, their quantum numbers are not that. The quantum numbers are -1, 0, and +1. There you go. But we say x, y, and z sometimes because of their orientation in space, right? One x-axis, y-axis, z-axis. Okay. And each one of those lines can only have 2 electrons, spin up, spin down, plus 1/2, minus 1/2. So there's your answer right there. And on a test, if you don't have any wonky ones at the bottom, like 2 of the above, 3 of the above, none of the above, that kind of thing, then you can work your way down, and when you get to the right one, stop. Go on. That's assuming you know what you're doing. If you're taking a guess, then you have to go into the process of elimination. Try to narrow it down to 2 at least, then you have a 50-50 chance. So there are a number of test taking techniques. Some people are pretty good at it. They could come into a chemistry test and, maybe make a C with never had any exposure to chemistry before, based upon they're kind of like grifters, right? They read tests like grifters read people. Okay, 16. How many unpaired electrons are present in the orbital diagram for an atom whose electronic configuration is 1s2, 2s2, 2p4? Okay, these guys are already paired, right? Because there's only 1 orbital each, like that. But this one is subdivided into those 3 levels. And if you follow Hund's rule, then you have to say 4. Okay, 1, 2, 3, 4. Got to fill these 3, then you can go back and start pairing them up. So we have 2 unpaired electrons. That's why the answer here is C. Okay. Now, if we got into d orbitals, right? You had maybe d, I don't know, 7. How many orbitals can you have in this subshell? 5. -2, -1, 0, +1, +2. That's because, let's see. That's because the quantum number for D is 2. And then you have minus that number. And then increment by 1, -2, -1. This one, quantum number is 1, so it's -1, 0, 1. And this quantum number is 0, so it can only have 1. All right, so the 7 would be 1, 2, 3, 4, 5, 6, 7. You would have 3 unpaired in that, or whatever that happens to be. Let's see, 7. It could be 1, 2, 3, 4, 5, 6, 7. Could be cobalt. That's a possibility. Cobalt would have 7d electrons, based simply upon where it is in that defilling transition metals. Okay. There we go. Which of the following statements about a D subshell is correct? Oh, I didn't know this was coming up. It is found only in shells greater than 2. Greater than 2. Actually, greater than or equal to 2. Well, let's see. Hold on a second. Shells, not subshells. Okay. Shells would be the principal quantum number, right? You could have 1, 2, 3 on up. Subshells would be L's. So this one could be just 0 right there. This one could be, oh, excuse me. Yeah, this one could be 0 or 1. This one could be 0, 1, 2. There you go. Yeah, so that's right. Shells greater than 2. So it has to be 3, 4, and up. And that makes sense. If you follow the periodic table, you're filling s orbitals here at the principal quantum number 3. So that's 3s, 3p. When you get down here, you got 4s. But once you get into the transitions, you got to back up 1. Right? So this is 4s, and these are all 3 ds. Right? And you don't get any ds until you get to the 3rd principal quantum number. What your authors call shells, subshells, orbitals. I like this way better. But I didn't write the textbook. Okay, elements in group 4A. So let's look at our periodic table. Where's 4A? We got two ways to number. We got the old way, which is this way, and the new way, which is 1 through 18 across groups. Okay, 4A. The A's are always going to be either this alkali metals, alkaline earths, or these representatives over here. And these are the B's. The A's are these two and these S orbitals, P orbitals. Right? They're always Roman numeral with an A. So if you go Roman numeral 1, 2, that's 2 electrons. Roman numeral 3, that's 3 electrons. The first one goes in the P. Right? So if we have 4A, we would go 1, 2, 3. Wait a minute. Excuse me, 4. 1, 2, 3, 4. Okay. That could be carbon. It would be P2, 2 electrons in the P orbital. So there you go. Did I confuse anybody there? I almost confused myself. Okay, 19. Oops, too far. I think there are about 30 questions in this thing. Which of the following statements correctly describes the subatomic particle called a neutron? Well, first of all, it's about the same size as a proton. The second is neutral. That's why they call it neutron. So let's see, which one fits? Slightly less than a proton? No, slightly more than a proton. Not found in the nucleus? Wrong. Has a positive charge? Wrong. More than one correct? Wrong. None of them are correct. Slightly heavier than a proton, and it's neutral. Now, it's slightly heavier than a proton because we've learned from studies of radioactive decay that when you follow the decay of radioactive elements, you find that if they increase proton numbers, I don't have an example off the top of my head right now, but if you increase proton numbers, you get it by the decay of a neutron. And a neutron decays into a proton. And actually, it's an electron, but at this point we call it it's a beta particle. Okay. So that little extra mass that neutrons have comes from that beta particle. In case you're interested. But that won't be on the test either. And then plus, there's some energy given off, right? And Einstein said, where'd that energy come from? Converted mass. So some of that mass is converted into energy because these beta particles are very high speed, give lots of kinetic energy. Okay, where was I? 20. Which of the following statements concerning types of elements is correct? There are more noble gas elements than transition elements. Sorry. you got a whole gaggle full of transition elements, and you've only got these noble gases. So A is wrong. There are more S block elements than D block elements. Can't be, because you can only have 2 groups in the S block, and you've got all of these in the D block. So B is false also. You just have to know where those blocks are, right? These 2 are S block, these are P block, these are D block, and these are F block. There are more nonmetals than metals. Wrong, it's the other way around. There are a whole lot more metals than nonmetals. You just follow this. In this periodic table, it's a red line. You just go down red, 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 red like that. All are non-metals, all these are metals. So most of the periodic table is metals. And there's no correct response. They're all false. How about, we got another one of these. Characterize each of the following statements as true or false. Well, let's see, maybe we can gain something from this one. It doesn't take too long. Let's go up a little bit. There we go. All the major minerals in the human body are metals. All the major minerals are metals. No. I mean, what about carbon? What about oxygen? What about hydrogen? Right? We're water bags, right? So we got dihydrogen monoxide, which is water. I saw there was this, it was a spoof, this document floating around, actually probably 20 years ago now. It was back when the environmental movement was starting to gather steam, and somebody created this one and said, we found a new pollutant on Earth. It's called dihydrogen monoxide. And they started giving all these things that it could do. And I mean, if you didn't know, you would like panic. It's like Orson Welles when he, War of the Worlds, when he did that radio show, and people started jumping out of buildings and windows. They thought the Martians were really attacking. People really, some people thought that dihydrogen monoxide was a deadly poison. It's water. Anyway, so that one's false. Iron is the most abundant transition metal in the human body. Iron, transition metal. Let's see. Transition metals are right here. Let's see. There's a pretty good bit of iron, right? Where's most of the iron located? Take a guess. Blood, yeah. Red blood cells. Mm-hmm. So that's probably true. I'd go for that. Deuterium is an isotope of hydrogen in which 2 protons are present. I don't think so. 2 protons makes it helium. Okay, so yeah, I think that was right. Most abundant transition metal is iron. And that gives you only one true answer. I've been watching lives of stars recently. How they form and what you can form when they die. And it turns out in stars about the size of the sun or a little bit larger, they start making elements, right? Start with hydrogen and a little bit of helium. They believe the original ratio of hydrogen to helium in all stars was 75% hydrogen, 25% helium. And they start cooking the hydrogen first because it's easiest to make helium out of. And then when they made all this helium, then they start pushing the helium together and making heavier elements. Well, as long as they can make heavier elements and get energy from them, then they can keep the star from collapsing, because there's a fight between gravity and energy pressure that keeps the star from collapsing in on itself. But when they get to iron, when iron is formed, you get no energy out of it. So it's actually a poison. It doesn't produce any energy that can hold the star up. So the star just goes in a matter of seconds once it gets to that point. And then usually the end result of that is a supernova. And depending on how big the star is, what's left over could either be a neutron star, and I don't have time to go into why that is, or a black hole. Anyway, why did I get onto that topic? I don't remember. Choose the correct atom that has a nuclear charge of plus 17. 22. A nuclear charge of plus 17. So what does that mean? That means 17 protons. Which one has 17 protons? If you're only talking about the nucleus, then yeah, it's charged, depending on how many protons. So 17 would be chlorine, wouldn't it? We just talked about that. All right. Choose an appropriate pair of elements that have similar chemical properties. Right? This requires you to use your periodic table and look in the groups and see which ones of these are from the same group. Let's see, rubidium and strontium. Got to be able to find them. Rubidium is an alkali metal. Strontium is an alkaline earth. Right? They're neighbors. They're not the same family. So they won't have the same characteristics. So it's not this one. Nitrogen and lead. That was a no-brainer. Nitrogen's a non-metal and lead's a metal. Okay, how about fluorine and chlorine? Aha, they're both halogens, right? They're in this family. Yeah, fluorine and chlorine. They have similar characteristics. They're never exact, right? Because all elements are unique. You can only say that they might be similar to another in their group. And then we found our answer, so we don't need to go to molybdenum. Molybdenum and which one is this one? Is that rhenium? That's not rhenium, is it? That's rhenium. Where's Re? That's Ru. Where?
Do you see the W? And 7, yeah.
Oh, okay. What is that? No, W is tungsten. It's the Latin is wolfram. Re. RH is rhenium, I'm sure. It's Re. It's going to bug me until I figure it out. Well, I'll have to live with it. Maybe it'll come to me. Okay.
Or E is rhenium.
Rhenium? What's RH? Rhodium?
I'm looking forward to that. Okay.
Oh, well, I got one in my phone. Let's see. Where, there it is. There it is. RH.
Rhodium.
Rhodium. Yeah, okay, here we go. Rhenium is Re. Rhodium is RH. Okay. All right. Scroll time. Let's see. There we go. 24. Which of the following is a property of both gases and liquids? Gases and liquids. Well, let's see. Well, let's put solids in there too. This is a definite shape and definite volume. This one's definite volume. Definite volume. And this was indefinite shape. Indefinite shape. That's it. Indefinite shape for both of them. But gas has indefinite volume also. So indefinite shape is characteristic of both gases and liquids. If you think about it on the molecular scale, they have indefinite shape because the intermolecular forces holding them together is not strong enough. They just sort of slide past one another. In liquids and in gases, they're too far apart to care about anybody else. Which of the following statements about heterogeneous and homogeneous mixtures is correct? Okay. It is possible to have heterogeneous mixtures Well, first of all, what's a heterogeneous mixture? You start with pure substances, and then you put them together, but they don't react chemically to form, to change the identity of those substances. They're just kind of in the same space, similar, they're close to each other. So a homogeneous mixture is where everything is uniformly distributed. No matter where you subsample, you always get the same ratio of pure substances. Heterogeneous is obviously, you take a sample and you get a ratio. And you take a sample over here from the same lot and you get a different ratio. That's heterogeneous. Okay, it is possible to have heterogeneous mixtures in which all the components are liquids. Yeah, that's true. Yeah, just think about booze, ethanol and water and other stuff as a homogeneous mixture of alcohol and water and some other things. A homogeneous mixture contains visibly different parts or phases. No, the characteristic of a homogeneous mixture is everything's in the same phase. Even if you have a gas homogeneously mixed with a liquid, they're in the same phase, they're liquid phase, even although the gas is dissolved in liquid. C, all of the phases in a heterogeneous mixture must be in the same state. Well, no, heterogeneous mixtures can be any combination. You could have a fog would be condensed water droplets suspended temporarily in air, gas and liquid, but they're not uniform. No two phases in a heterogeneous mixture can be in the same state. Yeah, they can. They can be in the same state. So the only one that's correct is the first one. You could have two solids mixed together here, but they're heterogeneous. Like, from my background, mixed fertilizers. Have you ever seen a bag of mixed fertilizer? Thrown it out on your garden or field. Yeah, if it's got nitrogen, phosphorus, and potassium in it, it'll usually look like there'll be little white frills. That's the nitrogen, and then the potassium. The phosphorus will be little gray granules usually, and then the potassium will be kind of translucent white and maybe some red mixed in with it. But they're all solids, and they're heterogeneous. And all you have to do to prove it to yourself, actually, if you've got time, you just take a sample and pour it in a clear, say, graduated cylinder, and mix it up real good before you put it in there, so it looks homogeneous. And then over time, just the natural vibrations from the earth will segregate the particles. And you come back 3 or 4 months later, and you'll see definite segregation of the particle sizes in there. Okay, that was 25, 26. Which of the following statements is correct? Elements but not compounds are pure substances. No, you can have a pure substance. Compounds can be pure. All you need to have a pure substance is there cannot be separated further by physical means. Okay, you could get down to a point where you have a mixture and you have this atom of, say, iron and this molecule of, I don't know, silicon dioxide, sand. And they're both pure because this is a pure compound and this is a pure element. So that one's false. Compounds but not elements are pure substances. Well, that's just another way of giving you a false statement. Both elements and compounds are pure substances. Yeah, that's true. Okay, 27. Consider the chemical formulas. Okay. Watch out. This is a tricky one. The chemical formula is this one and this one. It is true that they contain identical kinds of atoms. Is that true? No. That's cobalt, that's iodine. That's carbon, that's oxygen, and that's iodine. So A is false. They represent the same compound. Well, obviously not. I mean, they can't have different atoms and be the same compound. A, contain different kinds and numbers of atoms. Yeah, that's true. So that's why it's important to write your elements correctly. Right? I've had students claim that this is cobalt and this is iodine, but it's not. And many tears were shed. Okay, the total number of atoms present in one formula unit of this compound. Let's see, what do we got? CO2, SO4, taken 3 times. Okay, cobalt, sulfur, oxygen. All right, how many atoms do we have here? Well, we've got 2 here, right? How many sulfurs do we have? 3. Okay. How many oxygens do we have? 12. So that's 17. There's the answer. Okay. This is the polyatomic ion. That's why it has parentheses around it, because it behaves as a single unit in this compound. It has a 2 minus charge, right? It has 3 of them, which is 6 minus total. So that means with 2 cobalts that needs to be 6 plus total, each one is 3 plus. I gave you that one for free. 29, the description 2 substances present, 2 phases present is correct for 2 substances and 2 phases. Okay. A mixture of ice and water. No, they're the same substance, right? They're both H2O, right? They may be 2 phases, but they're not 2 substances. Okay. How about this one? A mixture of oil and water. 2 substances, yeah. 2 phases. 2 phases. Mixture of oil and water. Oh, I see what they mean. It's not necessarily that they're liquid solid versus or liquid gas or that. They actually are separated. They're the same phase, but they're separated from one another. That's what that means. And that's really it's not a good question. Because if it starts to confuse me, I can imagine what it would do to a student. But that's what they're getting at here, to say that this mixture has 2 substances, yeah, and they're 2 separated phases. We can stop there. How about 30? Which of the following statements about compounds and mixtures is correct? Both mixtures and compounds must contain 2 or more kinds of atoms. Yeah, compounds have to have 2 or more, right? How about mixtures? Well, if you have the same atoms, you don't have a mixture. So you have to have at least 2 different atoms. Yeah, so that one's true. More than one correct? No correct. Okay, so in that case, you would need to look at all of them in order to be able to eliminate D and E. Mixtures must always contain at least 1 compound. No, you can have elements. You have 2 elements together. We could mix argon and neon together. They're atomic. Both mixtures and compounds can have a variable composition. Compounds cannot. Mixtures can have variable composition. Compounds are fixed. That's the law of definite proportions. I think it was Proust that came up with that one. So no, one can, but the other can't. Okay, so now we can say this is the only good one right here. Let's see, we'll be getting close to the end of this one. Used up an hour and a half. In which of the following sequences of elements do all members of the sequence have chemical symbols starting with the same letter? Okay, well, let's see. S for sulfur, Si for silicon, Na for sodium. Right, so that one doesn't work. Let's say gold, Au, silver, Ag, aluminum, Al. Yep, that one works. What's potassium? K for calcium. P for phosphorus. How about lead? Pb, plumbum, which means heavy. Okay, so this one's it right here. Okay, we can still see this one. Which of the following statements concerning chemical symbols for the elements is correct? All chemical symbols start with the first letter of the element's English name. Nope, not always. Sometimes they're Latin. Most elements have two-letter chemical symbols. Yep, that's true. Technically speaking, if the single letter elements were not grandfathered in, then you theoretically, if you're working from English, you could get what, 26 of them? Right, 26 letters in the English alphabet. You could have single letters for all of them, but the history of naming elements and creating their symbols doesn't work that way. We have, let's see, nitrogen, and then we want to name nickel, right? So we don't want to give nickel some odd letter that has no basis in etymology of any kind. So yeah, so then we have to go from N to Ni to create a symbol for nickel. Or niobium in B. Are there any other N's in there? Neon. Well, sodium doesn't count because it's not based on that anyway. Okay, let's see. 33. Let's see if this one's worth wrestling with. Okay, I'll do 33. How many of these are true? The determination of a physical property of a substance causes no change in the identity of the substance. Yeah. Physical property has no impact on the identity of the substance. It refers to the potential, some type of potential for the substance. Matter is anything that has mass, occupies space, and can be seen by the naked eye. Well, not necessarily. Yeah, it's mass and occupies space, but right, an atom has mass and occupies space, but we can't see it. Two most abundant elements in the Earth's crust are oxygen and carbon. Half right. Not carbon. Two most abundant, oxygen and silicon in the Earth's crust. So only one of them is true. How about this one? Let's see, we want to tackle this one. A molecule is a group of two or more atoms that functions as a unit because the atoms are bound together by chemical forces. Okay, I'll go with that. Yeah, they function as a single unit. Crushing of ice to make ice chips is a physical procedure that involves a chemical change. That's contradictory in itself, right? It's a physical change, right? Not a chemical change. 2 is false. Most naturally occurring samples of matter are mixtures rather than pure substances. Yeah, I'll go with that. So 1 and 3 are true. I mean, just ask any, well, maybe not a miner, but whoever has to process the ore, they know it's a mixture from past experience. My goodness, we got a bunch of these, don't we? All right. When the formula for a compound contains parentheses, it's an indication that the compound is unstable and subject to decomposition. No, I don't think so. It's an indication that you have a polyatomic ion there. The fact that an unknown substance reacts with chlorine is insufficient basis for classifying the unknown as a compound. The unknown substance reacts with chlorine. Yeah, you can have elements reacting with chlorine, like pure sodium and pure chlorine react together to make table salt. It's a pretty violent reaction too. Right, so 2 is false. All chemical symbols use a 2-letter notation to represent the name of an element. Well, no. Well, none of them are true. This is said one of them is true. Oh. No, 2 is true. I was reading it wrong, correct? The fact that an unknown substance reacts with chlorine is insufficient basis for classifying it. Yeah, that's true. Okay. Anybody confused yet? All right. 36, the elements gold, lead, and bromine. For these elements, choose the appropriate characterization of the set's chemical symbols from the response list. Let's see. Gold is aurum, lead is plumbum, and bromine is Br. Okay, all symbols have 1 letter. No, all symbols have 2 letters. Yep. All symbols start with the same letter. Nope. All symbols start with a letter, not the first letter of the element's English name. That would be true for this one and this one, but that one starts with bromine's name in English. Right. So all symbols have 2 letters. It's the only one that's true. Let's see here. See how far we have to go. Oh, that's it for this one. I'm not going to do 37. Silicon, sulfur, and tin all start with S. Give the classification of matter from 38. When 2 substances are present as a heteroatomic, that's grammatically incorrect. It's not a heteroatomic molecules. What's the classification of matter when 2 substances are present as heteroatomic molecules? Well, you have to be a compound. Right? If you have 2, a heteroatomic, this would work backwards. Is it molecule? Well, if it's a molecule, it's got to have 2 atoms or more. Right? So elements can be molecules, compounds can be molecules. Right? The diatomic molecules, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, they're all diatomics. So they're not heteroatomic. The heteroatomic molecule has to have at least 2 different elements in the molecule. Like water. Right? So back to the question. What's the classification of matter when 2 substances are present as a heteroatomic molecule? Well, it's not a mixture, it's a compound. Right? If it's molecular, right, it either has to be a molecular element or a compound. That's the only possibility. Okay, a substance is melted. A substance is melted. Could be an element or a compound. Yeah, that's true. Right? You can melt sodium. You can melt sodium chloride, right, if you get it hot enough. In fact, there's some industrial applications of liquid sodium chloride, actually as a heat transfer medium. So liquid salt is circulated through nuclear reactors in some instances because it's a very efficient heat transfer medium. Could be an element or a compound. Yep. Could be an element, but not a compound. Could be a compound, not an element. Can either be, well, no brainer. It could be either one. Which of the following substance contains fewer atoms of one kind than other kinds? Fewer atoms of one kind than other kinds. Okay, let's see. Fewer atoms. All right, this has the equal numbers, right? So that disqualifies it. It can't have fewer because they're all equal. These are all equal, right? Same number of hydrogen as oxygen. And this one doesn't count because it's only got one type of atom in it. Right? So this is the only one that could be. Carbon is fewer than hydrogen, and which is fewer than oxygen. Right? That's not a good question either. I don't think. But it's the kind of thing you might see on a standardized exam. Because standardized exams are made by chemists who live in the bubble all their life. They don't get out and do real stuff like agronomists do. Okay, that's one of the documents. And how are we doing on time? 10:30? Did we talk about anything here that threw you for a loop? I'm talking about me, I'm talking about you. Let me take a quick look at the second document I have and just scan through it and see if there's anything in there that we didn't cover in this one. Okay, measurements, significant figures. Maybe we'll look at a few of these. Which of the following mathematical expressions correctly evaluated? All right, so I didn't give you guys that math quiz. Sometimes for my first semester general chemistry or my intro chemistry types, I give them this math quiz to see if you've got the math skills that you're going to need to do the course. And it has various operations and they get more difficult as you go. And this would be one of them. So if you have an expression like this, 10 to the third divided by 10 to the minus fourth, what does that resolve to? In the numerator, this is negative. But if you bring it to the denominator, if you bring it to the numerator, it becomes positive. And then when you multiply 10 to the fourth times 10 to the third, your answer is 10 to the seventh. Or the other way to look at it is, this one is 10 to the third minus a minus 4. Because in the denominator, you subtract the power of 10 to the denominator. Okay, everybody remember that? Okay, we won't have to stop at this one very long then. Let's see. How about number 10? After the 4s subshell, if you're going to go up to the next atom and it has an electron, where does that electron fit? Where does it go? So you need your periodic table for this one. to be the best way. 4s is where? 4s is here. So 4s1, 4s2. The next one is going to be 3d1. So the next electron will go into the 3d subshell. Okay. Let's see. All right. We know our elements. We have atomic number, mass number, charge, and number of atoms. So this one is equal to Z plus the number of neutrons. And so if you have this one, you got 14 atomic number, 14 protons, and not 27 neutrons. You have 13 neutrons. Contains an equal number of protons and well, that's true. Protons and electrons. It didn't say anything about how many neutrons you have. But if it's neutral, protons and electrons have to be equal. And if you form a charge, if you form an ion, how do you do that? Change the number of electrons. Can't change the number of protons, so you have a different element. But how many, let's see, if we started off with 14 and 27, 13 neutrons for this one. That's not the question, but I couldn't resist. Okay, let's see. I'm looking for new stuff. Remember our discussion of allotrope, what an allotrope is? An allotrope is an element that has a different molecular number. So for instance, gaseous oxygen, right? That's one form of oxygen. Another form of oxygen is ozone. Okay, those are allotropes of one another. Or carbon's a good one. You can have carbon, not graphite, not gas, but graphite. That's one form of carbon. Another form of carbon is diamond. Another form of carbon is, actually it has a number on it. This is Buckminster fullerene, otherwise known as a buckyball. And you have carbon with varying numbers as nanotubes. Those are all allotropes. Carbon graphite, they're using that in semiconductors. Once they can get a single layer of atoms, and the layering of graphite is hexagonal. So it'd be like this, like that. Each one of these is a carbon. And it just goes on. But it's a single layer. It turns out it makes an excellent base as a semiconductor, like silicon. But those are all allotropes of elements. Let's see. Let's get those. Looks like there's some redundancy in here too. Oh, this is, okay, the last one. Which of the following substances is both heteroatomic and triatomic? Triatomic means there are just 3 atoms. It could be O3 would be triatomic, but it's not heteroatomic. Heteroatomic means you need 2 elements or more. So triatomic and heteroatomic, this one would classify as that. Had 3 elements, 3 atoms, and 3 different, that are 3 different elements. 3 atoms and 3 different elements. This is diatomic. This was monatomic. And that one is triatomic. Let's see. No, it's not triatomic, excuse me. It's 2, 3, 6, hexatomic. 6 atoms. Okay, any questions? Concerns? Okay. So we can look at lab techniques. I did a little review, and it's recorded in and presented in Brightspace. But I thought I might just take a quick look at the stuff we're going to be doing. I'm not going to go into a lot of detail, but I do want you to have some orientation. Let me get rid of this. We'll turn this off. Actually, I can turn it on. There we go. Save the power on the bulbs. And we can look at laboratory techniques. So every lab has a purpose. Every experiment should have a purpose. Right? If you're doing it for, even for yourself or for a company, right? You're responsible to somebody. You need to know why you're doing it. Otherwise, why should you expend the energy and money to do it? So laboratory techniques, the whole purpose of this lab is to give you some hands-on experience with various types of measurements that we'll make in the lab. We'll measure length, and then we'll use those measurements to calculate area. We'll also measure volumes, and we'll use those to calculate, let's see, uncertainties. So in order to do that, you need to know what's the accepted value. So you can compare your measurement to that one. We'll measure masses. And for this, we'll compare balances. And we'll measure temperature. And we'll convert units. Okay, so those are the 4 activities that we're involved with today. Oh, I left one out. We'll, let's see, what would I say? This is not really a measurement. This is, we'll play with fire. Use a Bunsen burner. Learn how to play with fire responsibly. Okay, so let's see. There's discussion in here about, well, for instance, when we play with fire, we're going to use a Bunsen burner. That was named after an early chemist who decided that rather than use an open flame like a candle, which is basically what they had, gas was starting to be produced now in abundant and piped to various locations. And he needed in laboratories, he wanted to devise a safe way to use it. So he invented the Bunsen burner. Another scientist got involved, Tyrrell. Have some burners that are named Tyrrells. And then there's another one called a Fisher that you might run across. And it's hotter than either one of those. But they're all based upon natural gas as the fuel, and they mix air with it. And you control the mixture, the ratio of fuel to oxidizer, which is the air, oxygen. And that's how you develop the ideal flame, or the flame that you want. So in a Bunsen burner, what you're looking for is you're looking for a flame that has a structure like this. It has a double cone. And the inner cone right here, the inner blue cone, that's the hottest. If you have this structure, then this is the most efficient arrangement. You don't have too much oxygen, you have too little oxygen. If you have too much, if the fuel ratio is rich, you say. I don't know if that comes from them, but the first place I heard rich versus lean had to do with the internal combustion engines. When you set your carburetor up, either rich or lean, it refers to you have too much fuel for the amount of oxygen you have. So the fuel can't completely react and combust. So you have incomplete combustion. Complete combustion in your burner on the chemical basis should have methane, which is the primary ingredient of natural gas, mixed with oxygen, yields carbon dioxide and water. And if the ratios are proper, then that's what you get. But if you restrict the amount of oxygen, it's called limited. It's the limited reactant. Then you'll have this one, and it won't go all the way to that. It might go only partial carbon monoxide. Or maybe even less, it might go to graphite. And that's what we call soot. That's what you find in your chimneys. Well, along with some other stuff. And that's why it's dangerous to have a buildup of soot in your chimneys, because it's not completely combusted, right? If you have enough oxygen in there and you have an ignition source, your chimney can catch on fire. So what would a flame look like? Well, a flame that's incomplete combustion would be usually a lot bigger, like that, and it's kind of yellow. Okay, it doesn't have any structure except for this difference in color. Why is it yellow? Well, you get this soot, this incomplete combustion, this carbon, and you heat it up. What happens when you heat something up? It glows. So it glows yellow in this case. That's your soot glowing yellow, or incomplete combustion. Now, if you go the other way around, you have too much oxygen, then as long as the flame is still burning, you'll get complete combustion with extra oxygen left over, but you won't get that nice structure. In fact, if you go too far, it'll blow it out. Okay, so that's your burner. And you're going to stick some stuff into that flame and observe. Like you have a Pyrex tube with a holder, you stick it in there and say, what happens? Observe what happens. Usually either one of two things happens. You get condensation from the water. Gaseous water condenses on a cool surface. Right? Or if it's the yellow flame, you could get some dark buildup on the tube, right? The soot could collect on it. So things that you're looking for. Okay. So we learned how to adjust a flame. And by the way, first thing you want to do is set up your hot plate and put some water on it, and get that water starting to boil. So it'll take a while. And I've got ice. So you're going to measure temperature of boiling water and ice water mix. One thing about when you have water, liquid water, together with solid water, ice, as long as you got both of them together, it's always at the freezing point. Only when this completely melts will the temperature start to change. But the boogaroo here is you're using student thermometers, right? So it might actually be at 0 degrees C, but your thermometer might say 2 degrees or 3 degrees because they're not high quality. Okay, so temperature and then boiling water. Right? As long as the water is boiling and you have steam and liquid water together, they will stay at 100 degrees, theoretically, 100 degrees Celsius. Right, so you want to get that started first. And then we're going to measure the mass of things. I think maybe Erlenmeyer flask. What's an Erlenmeyer flask? It's like that in 3 dimensions. It's a flask with a flat bottom, so you can set it on the bench top. Make all kinds of different flasks, but that's an Erlenmeyer. And then you have beakers, right? They're just, that's it, made out of glass. You have a graduated cylinder. That's a cylinder of glass with markings on it for volume. And they get bigger as you go up. And usually in milliliters. And they're designed based upon this so that you can say, what does it contain? Well, you read it off, it contains this many milliliters. Let's see, what else are we going to be looking at? We're going to be measuring lengths. Let's see, using a meter stick. So you have to know how a meter stick is marked off. Right, the whole meter stick, right, by definition, is a meter. So the whole thing is 1 meter long, but it's divided into centimeters are the big marks, and then between the big marks are little marks, millimeters. Okay. So you measure, you can just measure your this. When it says measure lab notebook, just measure the page, height and length. And then you're going to calculate the area. Let me look at the, let's see. And you need to show your calculations. They got lengths in centimeters, and then convert them to millimeters. So how many millimeters in a centimeter? 10. Right, so 10 times millimeters, centimeters will be millimeters. And then you have to calculate area. So if you're going from, so use an example. If say you measured 3 centimeters by 4 centimeters, right? The area would be 12 centimeters squared, right? Okay. What would that be in millimeters squared? You have 2 options. You can say 3 centimeters is 30 millimeters, and 4 centimeters is 40 millimeters. So multiply them together, what do you get? 1,200 square millimeters. Isn't that right? 3 times 4 is 12, and then 10 times 10 is 100. Okay, or you can go from here to here. But notice that it's squared. And when you do unit conversions, if you square a number, you square the units too. So if we were going to do this by dimensional analysis, we would say 12 centimeters squared. What do we know about the ratio? Centimeters here, millimeters there. There's 10 millimeters for every 1 centimeter. But that doesn't cancel all the centimeters. It only does one of them. So the trick here is to square them. Okay, so that squares this, that squares that squares this, that squares that. So now, this cancels, leaves you with square millimeters, and this is 100. So 100 times 12 is 1200. That's why I got 1200 millimeters. Okay? That's a common error. Forget to apply operators to the units of measure also. Okay. So that's measurements of length and calculations with them. Volumes. So how are we going to tell what our accepted volume is? Well, you just have to say what you think it is. If we have a beaker, a 50 milliliter beaker, but it's only marked off in 10, 20, 30, 40, then we're going to fill it up to 40, and we expect that to be 40. It's our expected value. Then you put it in a graduated cylinder because the graduated cylinder is more accurate. And you measure what is it in the graduated cylinder. Right? Well, let's see, if this is 100, that would be 50, and it should be in the neighborhood of 40. But suppose it only comes up to 39. That's the measured volume, and this is the accepted volume. So what's the difference? 1 milliliter. What's the percent error? The percent error is the difference, we call it the delta. The difference divided by the accepted. The accepted is 40. So it's 1 divided by 40, right, times 100 for percent, or whatever that happens to be. That's what, 2.5%, I think. So that's what you're going to be doing with volume measurement. Mass, you're going to make measurements of, I think, 3 objects. One is a quarter. Does everybody have a quarter? Do I need to loan you a quarter? I charge you interest. And then we'll measure a couple of laboratory things, like maybe a test tube and a Erlenmeyer flask. We're going to use 3 different balances, right, with increasing accuracy from each one. We have the first 2 are triple beam. Well, they're like swinging arm balances. Right? So, have you ever used one of those before? Okay. And then there's one top loading balance, electronic balance. Unfortunately, the electronic balance, which should be more accurate, is about as accurate as the 4 beam swinging arm balance. But theoretically, when the question arises in here, which is more accurate, say the electronic balance. Okay. I guess I could have brought one with me, but it's not good to transport balances when you don't have to. Masses, volumes, length, temperature. Okay, that's it. I think that's everything that we're going to be doing. And you have report sheets here with some questions that need to be answered. See, they're pre-lab questions and they're report sheets for the actual lab. But the procedure starts, these pages are not numbered. 1, 2, 3, 4, page 5, it looks like. Bottom of the page, you start with a gas burner. How do you light a gas burner? That's a good question. Well, see, you have a stopcock, the main stopcock that sends gas through the tube to your burner. And then most of them have have slits in them like this. And then they have a sleeve that goes around like this. And the sleeve has slits in it too. And if you match up those slits exactly, that's the maximum amount of air that can go in. And if you turn it, you can block off part of that slit, and that decreases the amount of air. Most of them, some of them do have gas adjustment knobs on the bottom, but if they don't, you have to adjust it with the handle at the main gas source. Okay, so you turn it on and you hear the gas flowing through it, and then you take your striker or a match, depending on which we have, and the striker has a cup over it to keep it from flashing everywhere. But you have to hold it so that the flint is held tightly against the rasp so they don't make sparks. And then you hold it over there and it lights. If you use a match, right, you stand over it like this and you bring the match in here, right? It sends your eyebrows. No, you stand back, you light the match, and you come in from underneath and let it catch from here. Okay. That's a safety issue. Measure temperatures, degrees Celsius, and then you have to convert degrees Celsius to Fahrenheit, degrees Celsius to Kelvin. You can do that. And be on the lookout for show your calculations, because they're worth points too. And then there's some questions at the end, post-lab questions that you need to answer. For instance, number 5, post-lab. 2 students weighed 125 milliliter beaker that had a mass of 80.52 grams on a calibrated top-loading balance. That's a top-loading balance, is an electronic balance. And each student A, the balance student A used, gave those numbers, 80.560, 80.555, and 80.565. And you need to address this in terms of what's the average value in the correct significant figures. Right? So if you add all those together and divide by 3, you should only have 3 decimal places, 5 significant figures for both of them, whatever the case may be. And then you look at the spread, right? We're looking precision versus accuracy. So which one's more precise? You can just look at the spread of numbers and say, A is more precise. Right? It's tighter grouping. And then make value judgments about which balance is best in terms of precision and accuracy. Then on the next pages, we have some calculations that need to be done. Unit conversions. Probably the hardest one is going to be number 9. Because you got to compare masses in ounces, grams, and milligrams to the correct number of significant figures. And if you're comparing, if the mass of your glass is 8.3 ounces and you're adding 16.95 grams of sugar to it, what's the combined mass? Well, you can't add apples and oranges. You got to convert. So one time you convert to ounces, the other time you convert to grams. And once you get the mass in grams, you can convert it to milligrams too. So you need a conversion factor, don't you, for ounces and grams. Is that given to us? I don't know. Might have to look it up. I think we will have to look it up. Let's see, there's the formula for temperature. Here we go. On this page with that balance at the bottom thing, there's conversion factors. 1 ounce is 28.35 grams. So there's your conversion factor for answering number 9. Okay, any questions? We need to, I don't know. Everybody should have a partner, but we've got odd numbers. So maybe we just have one group. Just 3 of you work together and divvy up the labor, and you can knock it out. Okay.